When upgrading from knob and tube wiring to a modern electrical system, particularly when installing new subpanels, proper grounding and bonding are crucial for safety and code compliance. The specific question of whether to bond the neutral bar in the subpanels or leave it isolated requires a detailed understanding of electrical principles and relevant codes such as the National Electrical Code, or NEC. Considering a scenario where you are replacing old fused knob and tube panels without a ground wire, and the old system used rigid water pipe as a grounding electrode. You're replacing this with electrical metallic tubing, or EMT, connected to concentric knockouts on new square DMLO 125 amps 12-slot panels. There are 6 panels in total, operating at 120/240 volts with a 30 amps fuse main. You are using number 10 THHN wire for the feeder and bringing in a number 10 ground wire for a future upgrade to the rest of the system, connecting it to the ground bar in the new panels and to the main junction box. Every other panel is fed on one leg, using red wire, and the other panels are fed on the other leg using black wire, with only one neutral wire shared. The load on each panel consists of 9 incandescent 60 watts fixtures and a ground fault circuit interrupter, or GFCI, receptacle below each panel. The question revolves around whether to use the bonding screw for the neutral bar to bond the subpanels, or leave it out as an isolated system with the possibility of changing the luminaires to fluorescent fixtures in the future. Firstly, it is important to define the terms grounding and bonding. Grounding refers to connecting electrical equipment to the earth, providing a low impedance path for fault current to return to the source. This helps to trip over current protection devices, such as circuit breakers or fuses, in the event of a ground fault, minimizing the risk of electrical shock or fire. Bonding, on the other hand, refers to connecting all non-current carrying metal parts of an electrical system together, such as metal enclosures, conduit, and equipment frames. This creates an electrically continuous path, ensuring that all these parts are at the same electrical potential. In the scenario described, the old system used a rigid water pipe as the grounding electrode. While this was common practice in the past, it is no longer considered an acceptable grounding method according to modern electrical codes. Water pipes can be unreliable grounding electrodes due to factors such as plastic pipe sections, which can interrupt the electrical continuity, and corrosion, which can increase the impedance of the grounding path. The NEC requires a dedicated grounding electrode system consisting of items such as ground rods, ground rings, or concrete encased electrodes, often referred to as a U for ground. The new system incorporates EMT conduit in a number 10 ground wire. EMT conduit can serve as an equipment grounding conductor, providing a path for fault current to return to the source. However, it is important to ensure that all EMT connections are properly tightened and made up to maintain electrical continuity. The number 10 ground wire serves as a supplemental equipment grounding conductor, providing an additional path for fault current. This is especially important in situations where the EMT conduit may not provide a reliable grounding path, such as in corrosive environments or where there are loose connections. The installation of a dedicated number 10 ground wire for future upgrades is a prudent step. Secondly, let's address the question of bonding the neutral bar in the subpanels. According to the NEC, the neutral bar in a subpanel should only be bonded to the panel enclosure at the first disconnecting means, which is typically the main service panel. In other words, the neutral bar should be isolated from the panel enclosure in all subpanels. This is to prevent neutral current from flowing on the equipment grounding conductors, which can create objectionable current and increase the risk of electrical shock. When the neutral bar is bonded to the panel enclosure at multiple locations, it creates parallel paths for neutral current to flow. Some of the neutral current will flow through the intended neutral conductor, while some will flow through the equipment grounding conductors such as the EMT conduit and the number 10 ground wire. This can cause the equipment grounding conductors to become energized, which can pose a shock hazard. Furthermore, it can interfere with the proper operation of ground fault circuit interrupters, or GFCIs, causing them to trip unnecessarily or fail to trip when a ground fault occurs. In the scenario described, the subpanels are being fed from a main service panel. Therefore, the neutral bar in each subpanel should be isolated from the panel enclosure. The bonding screw or strap that connects the neutral bar to the enclosure should be removed. The equipment grounding conductors such as the EMT conduit and the number 10 ground wire should be connected to a separate ground bar in each subpanel. This ground bar should be bonded to the panel enclosure. The ground bar provides a common connection point for all equipment grounding conductors, ensuring that they are all at the same electrical potential. It is important to note that the NEC makes an exception to this rule for detached buildings or structures. If a subpanel is located in a detached building or structure, such as a garage or shed, the neutral bar may need to be bonded to the panel enclosure. This is because the detached building or structure may have its own grounding electrode system, and the neutral to ground bond is necessary to establish a reference point for the electrical system. However, in the scenario described, the subpanels are located within the same building, so this exception does not apply. Thirdly, consider the load on each of the panels, which consists of 9 incandescent 60 watts fixtures and a ground fault circuit interrupter, or GFCI, receptacle below each panel. The total load on each panel is 9 times 60 watts, which equals 540 watts. At 120 volts, this equates to a current of 540 watts divided by 120 volts, which equals 4.5 amps. This is well within the capacity of a 15 amps or 20 amp circuit breaker, which is typically used for lighting circuits. The installation of a ground fault circuit interrupter, or GFCI, receptacle below each panel is a good safety measure. Ground fault circuit interrupters, or GFCIs, are designed to protect against electrical shock by detecting ground faults and interrupting the circuit. They are typically required in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. NEC requires ground fault circuit interrupters, or GFCIs, protection for all 125 volts, 15 amps and 20 amps receptacles installed in dwelling unit bathrooms, garages, and outdoor locations. They are also required for receptacles installed within 6 feet of a sink or water source. Fourthly, let's address the possibility of changing the luminaires to fluorescent fixtures in the future. Fluorescent fixtures typically draw less current than incandescent fixtures for the same amount of light output. This means that the total load on each panel may decrease if the luminaires are changed to fluorescent fixtures. However, it is still important to ensure that the circuit breaker is properly sized for the load. The NEC requires that the circuit breaker be sized no larger than the ampacity of the conductors it protects. In the scenario described, number 10 THHN wire is being used for the feeder. According to NEC table 310.15 B16, the ampacity of number 10 THHN wire is 30 amps when installed in a raceway or cable. Therefore, a 30 amp circuit breaker is appropriate for this application. If the load on each panel is significantly reduced by changing to fluorescent fixtures, it may be possible to reduce the size of the circuit breaker. However, it is important to consult with a qualified electrician to determine the appropriate circuit breaker size. Additionally, some fluorescent fixtures may require a neutral connection, while others may not. It is important to check the manufacturer's instructions to determine the proper wiring configuration. Fifthly, let's address the distribution of the panels, with every other panel being fed on one leg using red wire and the other panels being fed on the other leg using black wire, with only one neutral wire shared. This is a common practice in 120/240 volts electrical systems. By alternating the legs that feed the panels, the load is more evenly distributed across the 2 legs of the service. This helps to prevent voltage imbalances and overloading of one leg of the service. The use of a single neutral wire for all of the panels is also a common practice. The neutral wire carries the unbalanced current from the loads on each leg of the service. As long as the neutral wire is properly sized to carry the unbalanced current, it is safe and acceptable to use a single neutral wire for multiple panels. The NEC requires that the neutral conductor be sized to carry the maximum unbalanced load. In a residential electrical system, the unbalanced load is typically calculated as the sum of the loads on all of the 120 volt circuits. The NEC allows for a demand factor to be applied to the neutral conductor size in some cases. This demand factor recognizes that not all of the loads will be operating at the same time. In summary, when upgrading from knob and tube wiring to a modern electrical system with subpanels, it is crucial to follow proper grounding and bonding practices. The neutral bar in each subpanel should be isolated from the panel enclosure, and a separate ground bar should be used for the equipment grounding conductors. The circuit breaker should be properly sized for the load, and ground fault circuit interrupters, or GFCIs, should be installed in areas where there is a high risk of electrical shock. The load should be evenly distributed across the two legs of the service, and the neutral conductor should be properly sized to carry the unbalanced current. Finally, it is always recommended to consult with a qualified electrician to ensure that the electrical work is performed safely and in accordance with all applicable codes and regulations. Number 10 THHN wire is suitable for 30 amp circuits, but confirm the load calculations for the luminaires and ground fault circuit interrupters, or GFCIs, to ensure it is appropriate. Also, remember to pigtail the ground to the ground fault circuit interrupters, or GFCIs, and then to the ground bar to maintain a proper ground.